We will now turn our attention to second order linear ODEs. So this is variation of parameters. This is 4.6. We can again take a linear ODE of second order and divide to get the leading coefficient to be 1. So divide this entire expression by a2. So we're able to write our second order linear ODE in the following form: y double prime plus p of xy prime plus q of xy equals to f of x. We know that from what we learned in section 4.3, we can very easily solve this for the homogeneous differential equation. So if we look at the homogeneous differential equation, y double prime plus p of xy prime plus q of xy equals to 0, we can come up with the complementary solution fairly efficiently and pretty easily, and it's going to be of the following form. It's going to be c1 times some function y1 of x plus c2 times some function y2 of x. Taking inventory of what we just did analogous to first order linear systems, it's fair to ask if we now return and revisit the non-homogeneous differential equation. How do we come up with the particular solution in this case? The answer to that is we want to ask the following question. Can we find y sub p by taking our complementary solution and once again kind of replacing these constants with functions of x? Will this actually work? So is y of p of the below form? In other words, we're trying to utilize our y sub c as much as possible in order to help us construct y sub p. And the answer is yes. This can be done. Makes sense that if you, again, by analogy, try to make some comparisons here. When we solved the first order linear ODE a while ago, we were able to come up with an expression for y sub p that involved one function u1. Now that we have a second linear order differential equation, we actually are going to have two functions we're going to need to solve for to find the particular value of y sub p. So ultimately, we're going to reduce the solution of y sub p to once again finding the complementary solution, which will contain two functions y1 and y2, and then y sub p will then be found by finding these variation of parameter functions y sub 1, u sub 1 and u sub 2. To get an expression that describes u sub 1 and u sub 2, we need to plug y sub p into this differential equation. So we're going to have to plug, y sub p into our full differential equation, which means we need y sub p's first derivative and also y sub p's second derivative. Okay. So let's go ahead and do that. And again, I'm probably going to drop the dependence on x. We know that u1, y1, u2, and y2 both depend upon x. When we do the first derivative, we need to use the product rule. It's going to be u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. So that would be our first derivative. Let's now go ahead and calculate yp double prime. Again, we have to do 4 product rules this time. We're going to have u1 double prime y1 plus u1 prime y1 prime plus u1 prime y1 prime plus u1 y double prime plus u2 double prime y2 plus u2 prime y2 prime plus u2 prime y2 prime plus u2 y2 double prime. we've gone ahead and we've taken all of those derivatives. Let's now go ahead and plug it into our differential equation. So the differential equation, it's y double prime, which I just wrote out. So we have u1 double prime y1 plus u1 prime y1 prime plus u1 prime y1 prime is that what's going on here? Yeah, that's correct. I guess maybe we should let's combine some like terms here. Otherwise it's going to get a little bit unruly. So we have u1 double prime y1 plus 2 u1 prime y1 prime, combining these two like terms. We have a u1 y double prime plus u2 double prime y2. These two can be combined. We have plus 2 u2 prime y2 prime plus u2 y2 prime. So we can write out 6 terms instead of 8. So u1 double prime y1 plus 2 u1 prime y1 prime plus u1 y double prime plus u2 double prime y2 plus 2 u2 y prime y2 prime plus u2 y2 double prime. So that's our y double prime. I'm now going to go ahead and write out p times y prime. So I'm already going to come over here to y prime, and I'm going to multiply everything by p immediately. So plus, we're going to have a p u1 prime y1 plus p u1 y1 prime plus p u2 prime y2 plus p u2 y2 prime plus the function q times y. So q times y would look like this. It's going to be q u1 y1 plus q u2 y2, and then this whole thing should be equal to f of x. Alrighty. Now is where the fun part begins. What we kind of notice is there's certain terms that have things in common. For instance, let me go ahead and combine all of the terms that have a u1 with them. So again, at the end of the day, let's keep our eye on the prize. We're trying to solve for u1 and u2. So I'm going to come over here, and any term that has a u1 with it, I want to factor out the u1. Where is my u1s? Well, there's one here. Oops. Here's a u1 term. Here's a u1 term. And here's also a u1 term. So if I take and I factor that out, then what's left? we're going to have a coefficient of y double prime plus, and I dropped the subscript there. What subscript was that? This is a 1, this was a 1, my apologies. That should have been a 1. So it's y double prime y1 plus, here we have a p y1 prime plus q y1. Now let's write all of the terms that have a u2 with them. Where are our u2 terms? There's a u2 term here, a u2 term here, and then we also have a u2 term here. Those coefficients, if I write them down, I feel like there's a derivative missing here. Hold on. Oh no, that's hold on. No, we're fine. So this is y double prime. So for this one right here, we have y2 double prime plus, when I factor the u2 out of this, we get a p y1 prime 2 plus, then this would be a q y2 and then we have the rest of these terms. So there's a few things that are kind of left over, if you will. And what we're going to do for those is, let me just write them out for the moment. I don't want to delete this because there's a important observation that's coming here in a second. So keep in mind, let me just write this at the bottom, y double prime plus p of x y prime plus q of x y equal to f of x, and yp, we're looking at it as u1 y1 plus u2 y2. So here's the thing about this. If we look at these terms, I'll write the rest of these here in a minute. But look at what we have. So when I grouped and combined some of these terms in the expression on the left-hand side of this equation here, remember y1 and y2, those are part of the homogeneous differential equation. Those are part of the complementary solution. So what that means is that both of these terms, right? So we remember that y double prime plus p y prime plus qy equal to 0 for both y1 and y2. So this term is 0 because y1 was a solution to the homogeneous equation, and y2 is also a solution to the homogeneous equation, so this term is also going to be equal to 0. So all of those highlighted terms, for that reason, drop out. And here's what we're left with now. We have u1 double prime of y1 plus 2u1 y prime, 2u1 prime y prime plus u2 double prime y2 plus 2u2 prime y2 prime, that remains, plus p u1 prime y1 plus p u2 prime y2, and this whole thing is supposed to be equal to the right hand side, which is f of x. We have 1, 2, 3, 4, 5, 6 terms left. 1, 2, 3, 4, 5, 6 terms left. And now with a couple of these, we can kind of try to write it a little more cleanly. And let's kind of make the following observation here. So the way that I'm going to group these, let's notice the following. So first of all, we have two terms that have a p in it. So I can factor the p out of these two. So we'll factor that p out. And that's going to leave us with the following. We're going to have a u1 prime y1 plus u2 prime y2. This equals to f of x. And we're going to group some of these other terms together. The terms in particular that we want to group are going to be the things that have like the u1s, y1s, and the u2s, y2s. So I think of these two as belonging together. And I'm not sure where I picked up this extra factor of 2 from. I'll have to go back and correct that later, but those two shouldn't be there. Plus u1 prime y1 prime plus, let's group these two, u2 double prime y2 plus u2 prime y2. And then the observation is that these two terms look like they kind of came from something that was like a product rule, and the answer is they did. This would have been the derivative of y1 u1 prime. Likewise, this second bracket, that would have come as the product rule for the derivative of y2 u2 prime plus p of, oh no, sorry, those twos were supposed to be there. Sorry. Those twos were supposed to be there. So what I wanted to do, there was no mistake here, my apologies. Those twos were there. I'm going to break one out. I'm going to group one in here, and then I'm going to add on the extra ones kind of at the end here. So we have extra u1, y1 plus u2, y2 prime. So u1 prime, and this are big old whiteboards we have in the college. But we got this. We have u2, y2, u2 prime, y2, plus these two extra terms, and we're just going to kind of group those together. So I mistakenly tried to say that those twos were not there. They were there, but I wanted to peel one of each off so I can make that total derivative we have on the left-hand sides. So we have an extra u1, y1 prime plus a u2, y2 prime. And this is supposed to be equal to f of x. And now, because these are both first derivatives, and the first derivative is a linear operator, we can take and write these as a linear combination. So we can think of it as one derivative of y1 u1 prime plus y2 u2 prime plus this p of x thing. Plus u2 prime y2 plus u1 prime y1 prime plus u2 prime y2 prime. And this whole thing is supposed to be equal to f of x. Okay. We have, again, at the end of the day, to find y sub p, we need to find u1 and u2. That's two equations we need to find. So we're going to, two variables we're going to need to find, two functional equations. So we need two equations for this. If we look at what we have here, the thing inside this derivative and this term also are the same. One equation we're going to get is going to come from assuming, and we can do this, and I'm going to kind of just claim it without proof, but it's true, that we can assume that this is going to be equal to 0. If that's the case, so if that expression is 0, then this would be 0, this would be 0, and then the second equation we get is that means under the circumstances that whatever's left over, this will have to be equal to f of x. So this is the derivation of the system. The y sub p, the particular solution that we're trying to solve for, is going to be found by taking u1 times y1 plus u2 times y2. And the u1 and the u2 are going to be found by solving this system of equations. I'll pause here, we'll stop right now, and in the next video we'll discuss how this system is solved for u1 and u2.